So today what we're going to be doing is looking at reflection and refraction, and we won't be doing a lot of calculations. In fact, just one example that involved calculations here. The purpose of this lesson is to familiarize yourself with what's called reflection of waves, and more importantly and more complicated, refraction of waves, so that when we get to Physics 30 we understand what's going on. I do have a demonstration that I'm going to show you though to begin with, and one of the things you're expected to understand in this unit is the concept of a standing wave, say on a string. So if I take a guitar string and I confine one end of the string to this point and one end of the string to this point, it can only vibrate with certain frequencies. And I don't know if you recall, but when we took that long, thin, coiled spring out into the atrium and I swung it around, I could only get certain standing waves because I had to keep up with a particular frequency. It's called a resonant frequency. So it turns out that if I were to take this string and pluck it in the center, then I'm going to get a standing wave with a wavelength a half the length of that string. It's going to oscillate up and down, and that's only half of a wavelength. Are you with me on that? It's possible for me, and whatever frequency that oscillates at would be the frequency we would hear. It's possible for me to take that string and pluck it around that point that I've indicated, which means I'm going to put my fingers on the string and I'm going to pull everything to the left of that point, say down, and everything to the right up. So I'm kind of twisting it with my fingers. And what happens is if I pull this side down and this side up and I let it go, then I end up with that situation. And that can oscillate that way because it's in perfect balance. One half of that string has kind of a natural resonant frequency to cause that part to go up and down, and the other half has the same resonant frequency because it's the same length. But I hope you understand that this is possible, and whatever frequency we hear, well, let me explain. This looks like a transverse wave, doesn't it? But sound is a longitudinal wave. It's pushing the air, producing a longitudinal wave which travels through your ears. That's possible, but if I were to say to you, and this has nothing to do with today's lesson, is this possible? Can I take my fingers and pluck it around that point and create this? And the answer is no. Because that left-hand part has to oscillate with a particular frequency to produce that shape, and the right-hand part has a different shape, so it can't oscillate with that frequency, with the same frequency. It would have two different frequencies on the same string, and it just doesn't work. So this is not possible. So if I take a rod, a metal rod, and I hold it, say, here, nothing. If I hold it in the center, you hear that? Is it possible for me to create music by holding it here, which is a quarter of the length? Well, it is, as long as it's a quarter. If it's a quarter, then I can get this going on. So if I hold it there, can you hear that? It's very... It's actually annoying to you, is it? If I marked it off in eighths, I could do eighths as well. If I marked it off in sixths, I could do sixths. This one is marked off at the halfway point, I believe. I don't think it's got a quarter notch on it. No, it doesn't. But if I try that and I hold it someplace else, well, I'll try a quarter. I don't know if I can get a quarter going. I'd have to know exactly. Yeah? You could hear it?
Yeah.
Really?
Yep.
Very high pitched, apparently, by the look on Alex's face. You can hear that, eh?
Gone for it's only dead for a bit, but it is existing.
If I try here, anything? I'll have to see if I can put quarter notches on this.
Not anymore.
No? You have to find the exact length, the place where there's a quarter. And if you look carefully on here, there's a notch on it. So I can tell where a quarter is on this one. Is that annoying? Oh, it is, eh? All right, when all the kids are playing around on the street outside my house, I can go out in the yard and see if it pushes them away. Okay, so I just thought it was an interesting little demonstration. We're going to be looking today at what's called reflection and refraction. And there are just a few things that we need to cover here. Okay, so what are the three things we need to know, and what are the three things we're learning today? How to describe the changes that occur when waves refract. That's going to be the second thing that we cover, even though I've listed it first on your handout. And refraction of waves is absolutely crucial for something in Physics 30, refraction of light. Then we're going to be talking about the difference between reflecting wave pulses and reflecting entire waves. And there's a difference here between what's called a wave pulse and an actual wave. Okay, and we'll get to that. But to begin with, when a wave pulse strikes a surface or a boundary between two different media, there's always some reflection of the pulse. So what do I mean by a pulse? I mean, if you were to take that spring that we had out in the atrium, and I think you remember this, Alex was on the floor holding one end of it, and when I caused a wave pulse to move down the spring, it hit Alex's hand and then it reflected back towards me. And you're expected to know how the pulse reflects if the end it reflects from is free to move, and if the end it reflects from is not free to move. Now, I don't know if anybody remembered this. You know, maybe we can just do it quickly in here. I have one of these still. Well, let's just take a quick trip in the hall. It will only take a minute. Thank you. Down on the floor, please. We'll try it with this first, and then we'll try it with the slinky. I think the slinky will work better, but I grabbed this one first. So I'm going to pluck this to my right. And it happens very quick. Okay? But I want you to notice the pulse is on your left when it's going towards you. And then what happens to the pulse when it hits back? It goes on the other side. And the end you're holding is not free to move. I can't really come up with a way to show you this where it is free to move, but if it were free to move, then what you would discover is it would come back on the same side that it reflects from. Can you let go now? And there's a physical reason for that. Let's head back in there, and I will see if I can come up with a demonstration to show you the reflection if the end is free to move. But first, let's write down an answer to this first question, or sorry, to the second question. describe how the reflected pulse compares to the incident pulse. Incident is the pulse that's going towards the fixed point. Reflected is the one that comes back. If the end is not free to move, the pulse reverses orientation. I have a very short and somewhat blurry video clip to show you. And it's on a loop. It'll repeat. So this is in slow motion, and I'll talk about it again in a second. But here it is at regular speed. You can see that there's a crest traveling to the left, and then afterwards it's a trough traveling to the right. So here in slow motion, this is what I'm pointing at right now is the crest, and then that part of the wave is below. So what this person has is not a spring. What they have is a whole bunch of metal rods that are attached to some kind of pivot point along the center. If I show you the same kind of idea where the end is not fixed, the end is actually free to move. We'll wait for it to start again. So here's slow motion. There's the crest up top. Afterwards, the crest is still up top. And you can see, if you watch this end right here, that end moves. So this is one of the things that we need to know. If the end is free to move, the reflection is going to produce a wave which is oriented in the same direction as it was to begin with. I prefer to just kind of think of it this way. I know the answer to number 2 is it flips because reflection involves changing direction, doesn't it? But when you reflect against something that does not move, everything has to change direction. So if the pulse was above that horizontal line in the video, or if the pulse was to the right of where I was in the hallway, and it hits something that's rigid, everything reflects. Not only does it come back towards me, but it reflects in that other orientation as well. So how is a reflected pulse comparing to the incident if the end is free to move? The reflected pulse is oriented in the same way. In the same direction. A lot of these little pieces of things that we're learning in this unit, and this is especially true here, don't seem to really go anywhere. Like we learn, okay, that's important for knowing how pulses reflect. We can certainly use that to explain why we get standing waves in that glass tube when we did the speed of sound lab. But it doesn't really seem to go anywhere. Most of what we learn in this unit does go somewhere next year in Physics 30. Okay. So now what about reflection of waves in general? Well, if anybody's played pool, you understand the concept of reflection is that when a ball hits a bumper on a pool table, it reflects off of that bumper in a particular direction. And generally speaking, the ball bounces off of the bumper in the same but opposite direction and angle as it had when it hit it. Okay? And that's going to be called the law of reflection. We'll get to that in a second. But we have to talk about something called wave fronts and wave rays. And now things start to get a little bit more abstract. First of all, what a wave ray is a line showing direction of wave motion. Are you with us? Okay, just checking. You okay? Yep. It's a line showing direction of wave motion. And it's not what the wave actually looks like. It's just a line that you draw saying the wave is traveling that way. Wave fronts are lines that have the same disturbance, I will say. Of the medium. What on earth does that mean? Well, there's a box beside these with an arrow to it, and we're going to add something else in that box to help us understand what's going on here. So first of all, a wave front is showing me what I would see. And I'm going to ask you to think of water waves when we talk about this. Okay? Sound waves are really nice to talk about, and they're interesting to do demonstrations. But they're longitudinal waves, which are more difficult to draw. And you don't see sound waves. You can see water waves, right? You can look out on the ocean, and you can see some waves. So a wave front is a line that has the same disturbance of the water, if we're sticking with a water wave. If you look at a water wave, you can see wave fronts. You can see these lines. You cannot see a line on the water showing the direction the wave is moving. So, for example, if I were to take, and it's up to you whether you want to draw this first part or not. If I were to take a pool of water, and I have this, it doesn't have to be a big pool, it can be the size of this table up here. And I take a meter stick, this thing, and I dip it in and out of the water. I'm going to create ripples that travel from your left to your right. I think that's pretty obvious. So if this agitator is moving in and out of the water, then what you're going to create is a series of ripples. And these ripples will be evenly spaced as long as I'm dipping the thing in and out of the water regularly. We're going to be reviewing some concepts here that started off the unit in terms of mechanical waves. Let me ask you a question. What could I do? What could I do to make those lines, those ripples, closer together? Faster, higher frequency. And that's kind of a nice idea because, as a side note, speed of a wave equals frequency times wavelength. And the speed of the wave is determined by the water, so if I increase the frequency, the wavelength goes down. That's why when we talk in Physics 30 about waves like X-ray radiation with a very high frequency, they have a very short wavelength. Whereas radio waves with a very low frequency have a very long wavelength. So if I were to take a look at this now, in between these, I hope it's not lost on you that these lines are actually crests. When you look out and you see a bunch of ripples on the water, you're seeing the crest of the wave. So I hope it's not lost on you that halfway between these crests will be troughs. And this is something that we talked a little bit about on that previous lesson on diffraction and interference. I want to clean this up a little bit. It's my type A personality that's poking through here. I just want to make sure that things are nice and tidy. So what we're talking about here are wave fronts. These are wave fronts. Now you can quibble about whether the wave fronts are the solid lines or the dotted lines or both. I don't care. The wave fronts show lines with equal disturbances. So everywhere along, and there's no need to highlight anything here, but everything along this line has the same disturbance. The water everywhere along that line is raised above the equilibrium position in the tank. So those are what we would call wave fronts. And I don't really know that you need to show this, but I feel the need to explain it. If you could look at this wave from a different vantage point, it would look like this. That's what we are talking about. You catch my drift here? Okay. That's a wave front. What is a wave ray? This is a wave ray. These are wave fronts. This is a wave ray. And the concept of drawing this wave ray becomes important because if you draw wave fronts, it's more complicated to look at, which is really weird. We're saying reality is more complicated than we would like it to be, right? We don't want to look at all these lines. We want to talk in physics about a single line that shows which way it's moving. Now, if you were to go back and look at the previous lesson, give me a second to pull it up. Which dealt with diffraction and interference. And this is okay too, because we get a chance to review something that we, quite frankly, haven't been talking about in weeks. I told you that what diffraction is when a wave passes through an opening, it spreads out. Now, I have an awful lot of information on here, so let me go back to the state that this page would be in on your original handout. On your original handout, and this is from, I think, the Wednesday of that last week, because we had no school Friday and Thursday was canceled. We had this, and I told you that what diffraction of a wave is when a wave passes through an opening, it spreads out. You remember the conversation about me saying if I'm sitting on my floating mattress at this point labeled X, drinking my pina colada and reading my book, that my mattress still goes up and down a little bit, even though I'm not directly across from the opening that the wave is emanating from. Where will I be moving up and down with the most energy, which doesn't mean a greater frequency, by the way, it just means up higher and down lower. Where X, Y, or Z will I be moving up and down with more amplitude or energy? Z. And why? Less, and then less even at X, right? So that's diffraction. But I may have even said, here it is, the diagram is of a plane wave front. These are the ripples. And this is the wave ray. And then I ended up drawing this. And I think, based on my notes, it looks like we even wrote wave fronts and wave rays. Do you remember that? Yeah, I know it's been 2 weeks, over 2 weeks, but that's what we did. And you do need to know about diffraction and also interference. And by the way, that's what I have here, right? We even have the troughs. So this should not really be totally new to you. So those are wave fronts and wave rays. Normal line, angle of incidence, angle of reflection. What a normal line is, and this should be no surprise to you, a normal force is a force perpendicular to the surface. A normal line is a line perpendicular to the surface. So when I talk about reflection of light from a mirror, if the board is a mirror, the normal line is this line. It's a line perpendicular to the surface of the mirror. If I'm talking about a wave, a sound wave maybe, that's going to hit that metal bar right by Kai. Kai, can you point to that metal bar on this? Right. If I'm talking about a sound wave and I'm speaking in that direction and that wave is going to hit that metal bar and reflect off of it, the normal line, thank you, Kai, is this line. It's perpendicular to the surface. It has nothing to do with the direction that anything hits the surface at. The normal line is perpendicular to the surface. Angle of incidence is an angle between two things. And I hope you understand, all angles are angles between two things. An angle of elevation of the sun is an angle between the horizontal and my line of sight to the sun. I'm not looking at the sun because I like my vision. An angle in a triangle, an angle in this vertice of a triangle or vertex of a triangle is the angle between those two sides. An angle is always an angle between two things. It's between the incident wave ray and the normal. And again, all of these things may not seem that crucial in your overall understanding in Physics 20, but when we get to Physics 30, things become, well, elevated. I think you can kind of guess what the angle of reflection is. An angle of reflection is the angle between, sorry, I've been away a couple weeks, I'm forgetting how to write certain things on the board. Angle between the reflected ray and the normal. So we've introduced the concept of a wave front, which is actually showing you what's happening. And we've kind of springboarded off of that to a wave ray, which is easier to draw. And we've done that because when we talk about angles of incidence and angles of reflection, they are always measured from rays to the normal line. So on the diagram, what we have is a tank. This is a tank of water that we're looking at from the top, from above. Sorry about that. And I have a normal line drawn there. I know that on your handout it probably says something like reflector on the right-hand side, yes? Yeah? So that dotted line is the normal line, and we will almost always draw a normal line as a dotted line, okay? So the surface here is the reflector, and we're going to create a wave that's going to reflect off of the surface. What we're asked to do is draw the incident and reflected wave fronts and rays. Now, I'm not going to get you to draw everything here, but would you agree in general that if I take this cylinder and I dip it in and out of the water, I'm going to create a whole bunch of wave fronts. You can choose to draw a few if you like. I don't really care if you draw them or not. But what I don't want you to do is draw all of the wave fronts I'm going to draw. We're going to get wave fronts created, which are going to be, I guess, imprints or copies of that cylinder. And if I dip that cylinder in and out of the water with a regular frequency, those wave fronts are going to travel with equal spacings. And it's okay to draw these 3 or 4 wave fronts. That's fine. But what I want you to notice is that the actual wave will be traveling in this direction. And I think the arrow that I've drawn is more important, significantly more important than the wave fronts. The wave fronts are showing what we would see if we watched this happen, but the wave ray is what we can use in physics to do calculations and those types of things, and we do not see it. I hope that with a little bit of thought you can convince yourself that the wave fronts and the wave rays will always be perpendicular to each other. For water waves, for transverse waves. But the question is now, those are the incident, this is the incident ray, this are incident wave fronts. What will the reflected ray look like? Well, I didn't hand out protractors. You're going to have to eyeball it. But let me ask you a question before you draw anything else. Is that the reflection that's going to happen? No. If you've ever played pool, you understand the concept of banking a ball probably off of a cushion or off of a rail involves knowing that it's going to enter at the same angle that it leaves at. It's not going to reflect there. It's not going to reflect here. Now, if I asked you to draw in the reflected waves, I think you would agree that drawing in the wave fronts that are reflected is more difficult to wrap your head around. But if I understand the concept of kind of angles here with wave rays, I could take a protractor, I could measure this angle in here, and that angle in there, by the way, is the angle between the incident ray and the normal line. That's the angle of incidence. And I can see that that angle is 40 degrees on my diagram. So that means that it would have to reflect at 40 degrees. This angle that I have here has to match the angle of reflection. I'm just going to put a little dot here at the 40. Remove my protractor for a minute and draw in that. So I can adjust it now. I don't know how well I've drawn it. And I haven't given you protractors today. To be quite honest, it isn't because it's not important. I just forgot to do it. And I think handing them out right now isn't necessary. But you can see now that this, which is the angle of incidence, is equal to this, which is the angle of reflection. And now if I asked you to draw in the wave fronts, you have a fighting chance because they have to be perpendicular to the wave ray. So the wave fronts on the bottom of the diagram are traveling up and to the right. The wave fronts over here are traveling up and to the left, and they have to be perpendicular to the wave rays. It doesn't really matter how many I draw or where I draw them. I suppose it is important for me to keep them equally spaced as they were before. And that's what you're looking at. Again, I keep repeating myself, but I think it's important you understand the motivation for learning these things. This is not necessarily the work that I would test you on in an exam. We'll get to that in a minute. It's about what we're going to do with it next year. Because Physics 30 is packed with material, like packed. So the more preparation we do for Physics 30, the better off we'll be. How many of you are planning on taking Physics 30? And do not be offended if you say no, doesn't matter to me, most of you, okay? So we've drawn the incident and reflected wave fronts and rays, and we've labeled the angle of incidence and the angle of reflection. Done. What do you notice about the angles of incidence and reflection? Well, this is the whole point. They're equal. Okay? When you play pool, the ball is going to bounce away from the cushion at the same angle as it has when it hits the cushion, as long as you don't put any untoward spin on the ball, which you might want to do if you were actually playing pool. If you put a left spin or a right spin, that's going to change things. which are easier to sketch. So, well, let's write this. Theta I equals theta R. Which are easier to sketch, wave fronts or wave rays? Wave rays, without a doubt. If I would have just started off by saying we've got a laser light that's going to hit a mirror, and this red line with the arrow on the end of it is the beam of light you can see in the cloudy room, it'd be very easy to understand what's going on here. Which are more representative of what is actually going on? Well, what's more representative of what's going on are the wave fronts if it's a water wave. But if it's a light wave, wave rays. And that's what we're going to be studying next year in Physics 30. So, I have a feeling that my pages are out of order here, and I know why they are, I believe. No, I don't even have it here. So, we have an example. There it is in your notes, law of reflection is theta I equals theta R. A wave reflects off of three barriers as shown in the diagram to the right. Determine the angle of reflection of the wave at barrier C. So just to begin with here, I hope that everybody appreciates if I drew wave fronts on this, it would be a nightmare, wouldn't it? Because I would have at least 3 series of wave fronts, actually 4 series of wave fronts. For each of those wave rays, I would have a series of wave fronts. I don't want to have to worry about that. So the question is, what is the angle of reflection at the third barrier? You know what this is? Ultimately, this is a junior high math problem. We know that this line is perpendicular to barrier A, right? It's perpendicular to A, which means that these two angles have to add up to give 90 degrees. I'm not going to be showing a lot of work here. Which means that if that's 22 degrees, this angle must be 90 minus 22. And at some point, everybody in the room is going to be saying, you may not be there yet, why do we care? There's a simpler, quicker way to do it. Okay? But 90 minus 22, I believe, gives me 68. And 68 degrees, then, is the angle of incidence at barrier A because it's the angle between the incident ray and the normal line. But the law of reflection says that this must be 68 degrees. Would you agree? Because that's the law of reflection. But this is 90 degrees because it's between the normal line by definition, which is 90 degrees away from the barrier, which means that this little angle must be 90 minus 68, which is 22. So how many of you would have just said that that must be 22 right out of the gate? Okay, that's good. But there's a wrinkle to that. There's nothing wrong with it, but there's a wrinkle to it that we'll get to later. Now, how are we going to figure out information about this? Well, we have a triangle. As I said, ultimately, everybody, this is a geometry problem. We have a triangle. And triangles on a flat surface have angles that add up to 180. I say that because a triangle on a sphere, the angles don't add up to 180. If you're interested in that kind of thing, it's called non-Euclidean geometry. So I guess I would say that 180 degrees, take away the 110, take away the 22 degrees, will be a way for me to find that angle. 132 away from 180 gives me 48. Don't let me do all the work. 48. Now, do I have to do the following? Do I have to say, let me get my dotted lines going here. Do I have to say that that means that this is 42 because those two angles have to add up to give 90, And that means this is 42 because of the law of reflection, and then take 42 away from 90 to say that this is 48. Do I have to do that green stuff? No. I could just say, well, that other angle's 48. And now I'm back in the same boat that I was with the yellow triangle, but this time we're talking about this blue triangle. The three angles must add up to 180. So now I'm going to be taking 180 degrees minus 48 degrees minus 82 degrees. By my count, that gives me 50 degrees, which the diagram is clearly not drawn to scale, but that's okay. So this is 50 degrees, which means this is 50 degrees. So what is the answer to the question? No, it's not 50.
40?
It's 40. Because although we get used to the fact, going back to my diagram over here, we get used to the fact that this angle and this angle are equal. That's not the law of reflection. The law of reflection says this angle and this angle are equal. And an angle of reflection, by definition, is the angle between the reflected ray and the normal line. So when I take a look at my diagram here, this is the angle of reflection. Let me redraw that. This is the angle of reflection in there. And you might say, and I get it, oh, what's the big deal? I mean, I understand what's going on. That's true. But when it comes to certain applications in physics, if you use the other angle, you get wrong answers in formulas. It wouldn't happen here. So now we have to say that the angle of reflection at that third barrier would be 90 degrees minus 50 degrees. And I mean, I don't even know that you would need to show any work here. But I'll be honest, the only reason I'm really giving you that example is I need you to understand angles are measured from normal lines, and it is absolutely important that you know that. All right. Now we're going to be talking about refraction of waves. So totally changing gear. Not just changing gear, we've pulled over, we've got out of the car, and we're getting in a different vehicle. It's totally different, okay? They are connected sometimes, but not always. What a refraction effect is when a wave goes from one medium to a different medium, okay? So if I lined up a whole bunch of students, grade 1 students, pull them all in here, about 8 of them, yeah, exactly. And I'm going to have them to hold hands. I'm going to say, stand in a line, hold hands, we're out in the hall even. Don't let go. Okay, you know what grade 1s are like. And I grab the first little guy's arm and I start moving them back and forth like this, okay? I'm going to create a wave that travels down. Would you agree? It's like what we did in the hall, except I'm not just moving them to one side and back. I'm just continually doing that. And let's imagine that I've got them on a very friction-free surface. Maybe they're on rollerblades or something. Or maybe they're just very relaxed students. And their feet aren't actually moving, but their bodies are moving, right? I'm going to get a wave, aren't I? And then this last person, I get us to line up. I get you to line up. And you form a chain connected to them. That wave is going to travel from them into you. But the wave is going to be different. Things are going to change. One of the things that will change is the wave will travel slower. I think that kind of makes sense. That's what refraction is, and it's more involved than that, but we're going to use that analogy from time to time to explain certain things. So for example, here are some illustrations. When a sound wave travels from warm air to cold air, refraction will happen, because warm air is a different substance than cold air. Okay? The sound wave in the warm air will be different than the sound wave in the cold air. Things will be different. Happens with any waves. If a light wave travels from air to water, it experiences refraction. And one of the things, and you're probably familiar with this, one of the changes is the direction of the wave changes. How many of you have seen that? It's not really an illusion, it's just reality, it's what we see, that when you put a stick in water at an angle, it enters the water and then it's bent. Okay? The direction the light is traveling changes direction as well as other things. And the direction that most waves have will change when they refract. When water moves from deep to shallow water, we have refraction. So we're going to just explore today on the next page what refraction is. So I need us to turn the page and understand what this diagram is showing. Again, I'm going to be talking about water, but in Physics 30 we would take out lasers and blocks of glass and stuff like that and see refraction of light. And I may show that to you a little bit later today. So this time what we have is not a barrier, not a reflector. This solid line is a boundary between two media. Everything above that line, and I mean everything, all of this is the same substance. And everything below the line is a different substance. Maybe it's, the classic Physics 20 example would be deep water to shallow water. But it could be, if this were a light wave, that it's going from air to glass or air to water. And I have decided I will show this to you with a light wave in a little while before the end of the class, because I think it's important you understand what's going on. So we have that, which is called the boundary. Sometimes we call it the interface. Medium 1 is called medium 1 because it's the first medium the wave is going to be in. Okay? And medium 2 is the second medium. The normal line is not a line that's just perpendicular to the boundary on one side, it's perpendicular everywhere. So if this is a water wave, the wave can travel here and it can travel here. It can travel in any part of this diagram. So let's see what we are asked to do. On the diagram, the cylinder is dipped in and out of the medium, creating a wave that travels initially in medium 1. The wave enters into medium 2 as it passes the boundary. And I'm going to tell you right now, medium 2 is more dense than medium 1 in our warm-up, in this illustration. What does that mean? Maybe it's water to jello. Maybe it's a water wave going into jello. So I've made a block of jello and I've cut it nice and square so that it's a block like this stack of paper. And I've put it inside of a tank of water. And I'm going to get a wave going from the water, and it's going to hit the jello and continue in the jello. Okay? Maybe it's deep water and shallow water. Doesn't really matter. Why is the frequency of the wave in medium 1 the same as the frequency of the wave in medium 2? I want everybody to think about that. That is like me asking you, why, when I take little Timmy's arm, the first grade 1 guy, and I shake it back and forth 5 times per second, other than possibly brain damage, what I will produce as well is a wave in the little guys of frequency 5 hertz. I'm asking you, why will it still be 5 hertz when it enters the big guys? It's a very counterintuitive thing, because how many of you would have thought the frequency in the big guys is smaller because it's harder to move them around? It won't be. It'll still be 5 hertz. Does anybody want to take a crack at that? Jay?
Because, well, I was going to say like their arms are longer and stuff, but I don't know where I'm getting.
No. And by the way, these analogies I use are not perfect analogies. They're done to help you figure things out in the moment that you're doing on an exam when you're trying to think of something. Any other ideas? Alex? No. You know what it is? They're connected physically to the little guys. So I have Timmy, and then I have Sally. And then I have Raheem. And then I have Jenny. Okay? When I take Timmy and I rattle him back and forth 5 times per second, the reason why Sally goes back and forth 5 times per second is because she's connected to Timmy. And the reason why Raheem goes back and forth 5 times per second is because Raheem is connected to Sally. And Jenny's going to go back and forth 5 times per second because Jenny is connected to Raheem. This whole thing, when I showed you what a transverse wave is, and I'm going to increase the frequency a little bit here, and I start, let's delete that, and I start by putting a point here. That point is moving back and forth with a particular frequency. If I add a point right next to it, the reason why that point goes back and forth with the same frequency is the medium is connected there. And the reason why that point is sometimes a little behind and sometimes a little above the other point is it takes a short period of time for that energy to transfer from Timmy to Sally, or whatever their names were. Are you with me? So it doesn't matter. By the time we get over to the end, this poor little guy over here is still going to be going back and forth 5 times per second. He or she may not be going back and forth as far. There may have been some energy loss, but it's still 5 times per second. And that means that they're connected to, John, this big football player, and he's going to move back and forth 5 times per second. And I'm going to summarize the answer to this question by saying something that we often say when we talk about refraction. Frequency is determined by the source. I'm just looking at the clock here. We have about 20 minutes left or so. We're going to finish this lesson, but there will be no homework. Okay? Frequency is determined by the source. Listen, if I sit on the edge of a pier listening to my Viking thrash metal, and my toe is going in and out of the water 10 times per second, no matter where that wave travels in the water, the frequency is going to be 10 times per second because it can all be physically connected back to my toe. I'm the source of the wave. If you haven't checked out Viking thrash metal, I highly recommend it. What will happen to the speed of the wave as it passes between the two media? Why? So now it's a different question. How fast are the ripples going to, not how fast are they moving up and down, that's different. How fast are the ripples going to be moving left to right or through the medium when they enter the more dense medium? And sometimes intuitive answers, the ones that you think are obvious, are wrong, and sometimes they're right. The speed's going to decrease. The medium is more dense. It's going to take longer for that energy to transfer from one person in the wave to the next person, in my analogy. So the speed will decrease due to the density. Now I have to warn you about something here. This statement is true for transverse waves. But when it comes, and transverse waves in liquids and gases, but when it comes to solid materials, it gets more complicated. So if you go on and get a degree in physics, you'll be told otherwise in certain circumstances. Okay, so the frequency is determined by the source, doesn't change. The speed is determined by what the wave is traveling through. So since it's traveling through something more dense in medium 2, it goes slower. What will happen to the wavelength? Alex? It would decrease. So let's write that down first. How come?
Formula, since it's multiple.
You're like me. I want to look at a formula, yeah. If we have V equals F lambda, I'm assuming that's the formula you're talking about, and the frequency is the same, but the speed goes down, the wavelength has to go down. And we can put numbers in here if you like. Let's say the frequency is 10 hertz, and the speed in medium 1, and the speed in medium 1 is 2 meters per second. Can you do me a favor and calculate the wavelength? Just using the universal wave equation, I think you get 0.2. So the wavelength here would be 0.2 meters. Well, what about medium 2? Well, if we say that medium 2 is more dense, then maybe it's only traveling at 1.5 meters per second in medium 2, because it's going slower because it's more dense. But the frequency is still determined by the fact that my toe is moving at 10 times per second. And now what I get for lambda 2 is 0.15 meters, so I get a shorter wavelength. How many of you would have figured the wavelength is shorter because if the wave travels slower, the ripples will just be closer together? So there's kind of an intuitive way for you to reason that out. So when, and this is one of the things you need to know, when a wave enters a more dense medium, the speed and the wavelength go down. And they go down by the same factor. If the speed is only half as great, the wavelength will only be half as great. So you need to know that. The angle of incidence during refraction is the angle between the incident ray and the normal line. The angle of refraction is between the refracted ray and the normal line. Listen, the only thing that's different here is when we talked about reflection, this word right here was reflected. It's refracted. So sketch the incident and refracted wave fronts and wave rays on the diagram and label the angles. Okay. I'm going to go back to this. Well, again, I don't think, and you're going to see a full diagram in all its glory in a minute, I don't think you want to draw in all of the wave fronts. I'm going to draw in 2 or 3. These are incident wave fronts. And we know that the incident ray is perpendicular, and we draw it the ray that is, so it hits that point of intersection of the boundary and the interface. Now the question is, which way will it be traveling afterwards? And I have a number of options. It could be, and please don't draw this, it could be that it just continues in the same direction. Right? I mean, that's possible. Well, I'm not saying possible that it might happen. I'm saying that's one of your choices. Or it could be maybe what actually happens is it changes direction and travels more down towards the bottom. Or it could be that it does this. And by the way, there will always be some reflection. Don't draw this in. There is always going to be some reflection. And by the way, I draw the reflected ray that way to indicate that not a lot of wave energy reflects, but some reflects. If I stand on the edge of a pool and I shout down on the pool, some of the sound wave will reflect above the pool and some will refract in. If I shine a laser light into the pool, you know for a fact some is going to reflect off of the surface. Okay? But the question is, which of those 3 do you think it is? And there's a reason, and it's a very interesting reason. Very difficult to figure out. I think it's down to a 50-50 guess. I think you know it's not the blue one, right? Something's going to change. Otherwise, why would we be having this conversation? Jay, you want to give it a crack? Green. Sorry, no. It's not green. Alex?
Pink.
It is pink. Now, it may not be that severe, but it is pink. Way back before people were taught on computers and smartboards and stuff, this is the classic example that you would find in a physics class, talking 70s, maybe even earlier, is instead of having a whole bunch of wave fronts this way, what you have is a whole bunch of the original example that I've tweaked, and I'll tell you my tweak in a second. The original example had a line of people in a marching band. All lined up, all in a line, playing their instruments, marching in a line. And this is pavement, and this is 1 foot of the stickiest, dirtiest mud you can find. I think you would agree, maybe even 2 feet, that for me to walk through pavement is pretty easy. I'm not even through it, I'm on it. But I hit that mud and I'm going to slow down. Yeah? Okay. But what that means is that this person is going to slow down first before everybody else in their line, because they're going to hit the mud first. And it's like steering a vehicle. If I'm traveling in this direction that I'm indicating, and my right-hand wheel starts turning slower, my vehicle is going to turn this way. So what's going to happen is afterwards, the leading edge of this ripple hits this boundary first and goes slower, and as a result, it's going to bend. And I have an animation to show you. The analogy I use is, imagine that this is an axle with 14, 15, 16 wheels on it, and I roll it in that direction. When it hits that dense medium, that first edge of the axle is going to slow down and the whole thing will start turning. So this, and it's a little hard on the eyes, is what we're talking about. Now, I have this, I'm going to actually rotate it so it matches what we have. And I'm going to put in a normal line. Well, here's my boundary. And here is my normal line. Make this a little thicker. Here is my normal line. And by the way, it also explains why the wavelength has to go down. The lines are closer together, aren't they? So this line, I mean, it's in motion, so I can't really do anything. But this line here that's moving, it's moving, it's moving, it's moving. This leading edge hits this dense media first, so it goes slower, and then everything else catches up, but at a later period of time, so the whole direction changes. So let's finish this off now, and I will tell you what it is you need to know. Where we left ourselves is sketching the incident and refracted wave fronts and wave rays and labeling the angles of incidence and refraction. So now we can do that. We know that if the wave travels from one medium to a more dense medium, it refracts like that. What we say is it refracts towards the normal. Less dense to more dense refracts towards the normal, slows down, shorter wavelength. So if I were to draw the wave fronts here, the wave fronts are going to be closer together. Finally, this is theta I, this is theta R. R for refracted. So what do you need to know? When we start talking about refraction of light in Physics 30, you need to know this. If it goes from less dense to more dense, wavelength goes down. speed goes down. Frequency stays the same and it refracts towards the normal. And that's what we have here. Less dense to more dense looks like this. More dense to less dense looks like that. V lambda, V lambda, smaller. V lambda, V lambda, larger. You also need to know on those diagrams where theta 1 is and where theta 2 is. Theta 1 is the same as saying theta I for incident. Theta 2 is the same as saying theta R for refracted. I think maybe some of you will appreciate why using 1 and 2 might be better than I and R. And the reason is R can mean reflected or refracted. So what I have here is a tank of water. The surface of the water is the boundary or interface. The normal line is this line here. And if I were to go from air to water, there's a beam of light. Water is more dense than air. I hope you would agree. The light refracts towards the normal. Explaining why that's happening is a lot different than explaining why water waves do this, because this is so far away from being like people in a marching band. You can see it, right? So far away from that and so far away from wheels and mud. It's an electromagnetic wave. It's different. Less dense to more dense towards the normal. More dense, it's going from the water now out into the air. It refracts away from the normal. In terms of refraction, this is what you need to know, as well as knowing that this is theta 1 and this is theta 2. You'll notice again, I switched from I and R to 1 and 2 in this diagram.